Hello, welcome back. Hope you enjoyed your lunch. This is the afternoon session. We got two talks, one on writing hardware drivers and one on the Kinect. I'm going to start with Chad on writing hardware drivers.
Hi, everyone. So often the first place you get to after you look at the ROS tutorials is, I want to put my robot in ROS, or you have a collection of hardware. So I figured this is a good introduction for what to do next and how to bring your hardware into ROS. So first, a little about me. I'm a robotics engineer at Carnegie Mellon's National Robotics Engineering Center. I am also a ROS driver maintainer for laser drivers, so the SICK and Hokuyos, and IMU drivers. And occasionally I even write stuff. I've written 2 Android apps, the Android Sensors driver, and that currently supports GPS and full IMU, and the Android Robot Monitor, which reports diagnostics, which we'll talk about later, onto your Android phone. So I'm going to go through 5 steps: starting your driver, writing the standalone library, writing a ROS wrapper, dynamic reconfigure, and diagnostics. So the first thing that you should do when starting your driver is make sure that you're not repeating anyone else's work, or that there isn't something similar that you can work together with someone on. So you should first search the ROS wiki, and if you find there's especially a good list of drivers here at wiki/sensors. I think we try to keep it up to date, and you can also search on ROS answers to see if anyone has asked for that particular piece of hardware, and if no one has, you can even ask, because sometimes people don't publish things. And if you do find an existing driver, it's usually best to collaborate to make one common code base with multiple efforts rather than multiple smaller drivers with fewer features. So one of the first things you should do is decide your language and platform for your drivers. So ROS has different programming languages that it supports. One of them, the first one, is ROS CPP, which uses C++. This is the high performance library, and I primarily use it on Linux, but I understand that it has some OS X and Windows support. And it also currently has the best diagnostic support and is the most documented. ROSPy is a prototype and easy-to-use language. It also recently got diagnostics support, which is a set of assistant libraries that can help you, and we'll talk about that later. And it, again, is Linux and some Mac Windows. One of my favorite newer languages is ROS Java, which we heard about yesterday, and that's written in pure Java with Android support, and so I was able to produce those apps. And then for completeness, there's also ROS Lisp and ROS Lua. I have never worked with these, but if for some reason you have existing drivers, you may want to look into them. So there are these things called ROS enhancement proposals, and these are sort of standards or collections of good ideas that we've documented and put out. And there are a lot of these that are relevant to hardware drivers. So one of the most important ones for me is standards of unit and measure and coordinate conventions. Because if your driver reports in a wrong frame, that can be very confusing for the rest of ROS. So these sorts of things document the best practices. So you have units of measure, camera info for camera calibrations and intrinsics, coordinate frames, diagnostic systems, informational distance measurements, so what to do when you can't report a measurement, depth images for sensors like the Kinect or stereo cameras, and coordinate frames for human robots for the driver for your humanoid. So the next step that you can do is to decide your ROS API. So these are things like your topics, your messages, your services, what you need to take in from the system and what you need to provide to the rest of the system. So the best place to look here is in standard messages, common messages, and standard services. These are packages that contain the most widely used APIs and messages for ROS. So you'll see things like geometry messages, nav messages, sensor messages. So these are your laser scans, your point clouds, your odometries, These are all API reviewed, and they are the best interface between your driver and your clients. For configuration, you have a few options. You can use parameters through the parameter server, or if you want a next better step, you can use dynamic reconfigure, which we'll talk about later. And then finally, you should use diagnostics. So here's an example API. This is one of the more complicated ones for cameras. There are two assistant libraries here. One's called image transport, and one's called image camera info manager. So image transport publishes a set of synchronized messages between sensor images and sensor camera info. And what this does is on the topics image raw and camera info, it publishes the synchronized sets for you. And it also includes helpful things like the pointer versions that you can use so that you can put this image transport directly into a nodelet. And then Camera Info Manager is an API that lets you use the calibration tool and then just hit the send camera info, and then your driver over a service receives the new intrinsics and immediately begins publishing them over the wire. This is helpful so that you can immediately check the quality of your calibration without having to bring down your driver and bring it back up. Not all drivers have to have this complicated of an API, but for cameras, it was a pretty good choice. So we can review here. So let's say, as there is right now, there's a new model of Fukuyo laser. So are there similar drivers? What languages and platforms would we like to support? And what messages should we use? So right now, as far as I'm aware, there's the Fukuyo node and the URG widget. And the Fukuyo node supports the older Fukuyos on USB, and the URG widget actually supports the newer networked ones, which is a good place to start for the newer model if you're looking to quickly prototype or test. These are both can be supported in ROSCPP, and you can see Linux and then maybe Mac and Windows support. The messages that we would use for this would be sensor messages laser scan, since this is a planar 2D scanner, and diagnostics for reporting the status of the driver. So another common one that people run into is your in-house mobile platform. So this is your base, your motors, maybe some wheel encoders. What do you do here? So we'll look for similar drivers again, a language and platform, and what messages that likely we should use. So similar ones are, of course, the TurtleBot, which is one of the standard, where do I look for a good example platform? And Pioneer also has a pretty good example of how to take existing hardware and move it into ROS. The language and platform is your choice, since this is your platform. And the messages that come from this tend to be pretty low bandwidth, so performance, you don't need to worry too much about that. And as for the messages, the common API is to use on CommandVel a geometry messages twist, which has velocities and angular velocities, and on ODOM, a nav messages odometry, and this is where your wheel encoders would be fused, and you would report how far you've traveled and your current rotation relative to where you started. And of course, diagnostics again. So the next step is, once you've decided how you're going to write your library and put it into ROS, is to do so. So one question that I had when I started writing ROS drivers was, why would I write a standalone library? I just want to get it in ROS quickly and be done. But if there's ever a chance for anyone to share or use your code, then that's better for you. So a standalone library permits other people to use your code, even outside of ROS, and it frees up your driver from requiring the ROS headers and ROS transports. This could lead to wider adoption, which means additional testing, which means less bugs for you to find, and sometimes they even provide fixes. And it helps you commit more to the wider community. One trick that was common and is even easier now is to actually use the message headers that are auto-generated inside of your standalone library. It used to be, I believe, that you would just copy them over and share them as compiled chunks, but I think as of Forte, they've worked really hard to make the message generation exist separate from ROS. So now that you can use these in your libraries completely freely. And speaking of dependencies, just like we would like to avoid ROS at this, requiring ROS at this stage, other mistakes that people make can be requiring large dependencies. So OpenCV and PCL are common dependencies that people require in drivers that really place an unnecessary burden. They reduce the portability of the driver because you may not be able to compile OpenCV on whatever versions of dependencies you have on your embedded system. And they can also make the driver unnecessarily complicated. So you can imagine that if we used OpenCV in our hardware driver, we would go first from the API we're using to grab the image from the camera into OpenCV's CVMAT format, and then finally to get that into ROS, we'd have to go to CV Bridge and then a sensor messages image. And that's pretty much 3 unnecessary steps. And just like we don't want to take those unnecessary steps, if you do keep changing representations, then you could make mistakes, because the more hops you make, the more of a chance that your representations weren't compatible. And also, for images, if you copy at each of those steps, you can have very high CPU usage. Another thing that you should avoid is using graphical components in your driver itself. So these are things like the PCL visualizer, the OpenCV visualizer, or any other graphics library. Lots of systems like to run headless, which means they don't even have the X environment installed or any of that. So they would have to fork your driver and then actually compile a different version. Or if you did that for them, that's more for you to maintain. And I always find this unnecessary because I use the existing visualization tools such as RViz, which means once you have your driver library compiled and sending to ROS, you can immediately check it using a known good visualization tool. So we can go over a little bit of a review here for writing a library. So which of these dependencies should or should you not use in a driver library? So CV grab frame, the boost ASIO, which is a C++ network and input-output library. I often use it for networking and serial. And finally, Qt, a graphical framework. We probably shouldn't use the OpenCV, since we should try to directly fill a sensor messages image straight from the library we're using with the camera. Boost ASIO, we could probably use. Boost tries to have significant portability between platforms, but if there's something better, then you should use that. And you should avoid Qt, because even though it's very cross-platform and portable, graphical components and drivers can mean that it won't be able to run on headless or embedded machines. So now, I've covered an overview of writing a library. Now it's time to actually put it in the ROS, which, if you did a good job with your library, this will just be a quick, simple implementation. So you can see here that I've mocked up a very simple use of a library inside of ROS C++. The first thing we would do is just initialize our library, and then while ROS is okay, just create an IMU message, fill it in with a library, and publish. And that means that your library has abstracted all of the complexity from ROS, leaving you free to create very simple debuggable ROS nodes. And this is just a quick overview of the steps that you should take when you write your ROS wrapper. So first you can init your node, which means talk to ROS, initialize your library. Then you can grab your parameters from the server and any configurations that you need to set your library how you want it. Then advertise, subscribe, do your work, and then make sure that you occasionally check in with ROS, and that depends on the client and threading model you chose. But as we talked about in yesterday's keynote, ROS doesn't really force a program structure on you, so you're free to use whatever you feel most comfortable with. One important part of your ROS wrapper will be taking your library, like if it throws exceptions, and providing that information to your user. So one of the primary uses of this is ROS out. So in ROSCP, this is called ROSConsole, and in ROSPy, you just use log warn or log error. This prints to both the console and a tool known as RxConsole so that you can view this remotely over the network. This is nice because this is your first line of defense in notifying your user of problems. So there's different levels. Debug is commonly only used for you. This is if you say you've sent 10 bytes on a port, or if you're trying to debug, you can say, I've reached this step in this stage. The user typically doesn't care about this information, and debug statements can flood them with unnecessary information. So the first level that they usually see is info. So these are nice things, like if your driver successfully starts up and connects, it's pretty good to tell them this. So you can say, I've connected on this USB serial port. And now the next 3 stages are all if something's gone wrong. So if you can do a warning if something is out of spec, or if there's a configuration that you think is a little funny that your users probably wouldn't want to use, but you can actually continue running, that's just the warning. It means the user should be aware that this is a condition, but they don't necessarily have to take action. Error is something more serious, which in large numbers or even a single one could indicate that there is something wrong with how the system's working. So for instance, if your serial port started failing checksums and your user saw this on the console, they might go over and realize that their serial port has come loose or disconnected. And then finally, the last one, which should be used most sparingly, is fatal. And this is when your node has absolutely nothing that it can do to recover, and it's going to close on its own. So this is something like if your platform's voltage is too low and you have to shut down to save your batteries, that's when you would use fatal. Now I'm going to go off on a tangent here and talk about a more advanced topic, which is the shared memory transport in ROS. And this is another stage to writing your ROS wrapper. So high bandwidth applications benefit from the shared memory transport. This is especially good for things like images, where you can be transmitting tens of megabytes per second. There's a lot of CPU that gets eaten up trying to serialize that and unserialize it just to transport it between nodes. So as we saw in the lightning talks yesterday, the nodelets let you pass shared memory versions. And ROS implements this using the boost shared pointer. And there's actually convenience aliases that you can use right off the bat. So if you just attach PTR to the end of your data type, that's all of a sudden the shared pointer type. Or you could go into the : PTR, and then that's the same alias. There's also const, which is nice for these nodelets since it is truly shared memory, and you have to be aware that if you change it in one nodelet, all the other nodelets will see that change immediately. But the nice thing about nodelets is that they are dynamically loaded at runtime. There are some differences between nodelets and nodes. So nodelets must be classes, and they have a class that they inherit from. They interface through ROS through convenience functions that are very similar to, but not exactly like what you see with nodes. So for instance, instead of just creating a node handle, you call a convenience function that's get node handle, and then you're passed a node handle that's already taking care of the remappings for your specific nodelet. So you see almost no change, even though all of your nodelets are running inside the same process. The interface is identical to what you would have for your node. So once you have your node handle, you just ask for your parameters, and then the private remappings and remappings all get applied for you. Nodelets also have one thing that you should be aware of when they are initialized, which is the onInit function, not their constructor or main. So this is called after they're loaded, and right before they start to do their work. So this is where you set up like where you want your callbacks to go. And then finally, nodelet doesn't use ROS warn, ROS error. It uses nodelet warn, nodelet error, so that you can have properly remapped titles to RxConsole. And I've already mentioned the similarities that you can still remap topics, read parameters, run from launch files, and nodelets can also be run in what's called standalone mode, or you can compile them into a traditional ROS node so that the user sees almost no difference and they can just sit and go ROS run, your nodelet. And they don't actually know it's a nodelet unless they need that high performance shared memory. So we can talk review about this. So if your driver cannot open a port, is this a debug, info, error, fatal? And if your program attempts to recover, which is a good thing, then it should be an error. So you can simply say, oh, I can't open that port right now. I will try in 1 more second. And if your program simply just says, oh, the port's closed, I'm bailing, then you can use fatal. And some review about nodelets. So if you have a stereo camera publishing images at 10 megabytes per second, should you implement a nodelet for this driver? And then if you have a laser scanner publishing scans at 1 megabyte per second, should you implement a nodelet? And of course, for the cameras, yes, you should implement a nodelet because shared memory can save significant resources. And at lesser bandwidths, it's up to you. I said maybe for the laser scanner at 1 megabyte per second. As we're seeing more and more smaller and embedded devices come into the ROS ecosystem, the CPU usage, serializing and unserializing that data could start to eat up the entire usage of that board. So anything that we can save is better. All right. So now I'll talk about one of my favorite tools in ROS, Dynamic Reconfigure. So Dynamic Reconfigure allows you to change parameters during runtime without restarting the node. This initializes parameters and stores changes on the parameter server, and I highly recommend it, and it's lots of fun. I may or may not dynamic reconfigure everything I can get my hands on, whether it should or not. Here I've shown an image of what the dynamic reconfigure looks like for the Hokuyo node. So you can see that you can set things like the minimum range. So this is a 2D laser scanner for those who aren't familiar. So it starts at one end, scans, and ends at another point. You can actually tighten up that range without restarting your driver. And then you can turn on the intensity returns, which is the amount of energy the laser gets back from its reflection, and that can eat up more bandwidth. And you can see here that you can even change the port. So if you launched your driver on your remote robot and went, oh, oops, I had 2 Hokuyos plugged in. I don't want this one, I want the other one. You can just change it right there on the fly. And it's really fun. Dynamic Reconfigure is good for user convenience and remote configuration, and it's great for changing driver modes, resolutions, and rates. It's also a great way to test the various modes and parameters, and if the node is running on a remote machine, Dynamic Reconfigure is more convenient than SSHing into the robot, changing your parameters, Control-C-ing your node, relaunching it, and then going back and checking your results. You can just, from your laptop remotely, open up Dynamic Reconfigure, change your little slider, and then your robot's all of a sudden using the parameters that you want to test. This makes iterations on it very fast. This is the example ROSPy API for Dynamic Reconfigure. So the part you actually start at is at the bottom. So we first just init our ROS node, and then we define our reconfigure service with just a config type, which is something that if you go through the Dynamic Reconfigure tutorials, you'll see that you can define the types you change a priori. And then you give this a callback. And then finally, when the user goes and changes something in the GUI, this callback triggers. So you can see here that I've set up something for the user to change the color of an LED. So they could have a little slider for a red, a green, and a blue channel. And then in the library, I just give it those values. And then I read back from the library what colors it could actually support. And then I return that to the user. So in this, less than, 10 lines of code, I've already set up a whole feedback loop between my driver and my user. And of course, this is a trivial example, but you can imagine it becomes more significant for things like laser scanners, where the user may not even know the ranges that the laser scan supports, but if they just try to max it out, you can correct it and say, oh, it can actually only go this far, and it's very handy. So here's a review on dynamic reconfigure. So should you use this for controlling a camera's frames per second, for changing a motor controller's configuration, and for changing a publisher's topic? And for camera frames per second, yes. So this helps your user, so if they're trying to log and they realize, oh, the camera's outputting too fast, I need to turn it down. Or even if they can't keep up with the processing, this helps. Oh, am I too soft?
Hi there.
Thanks. Hi. Well, now I'm stuck. My track, I'm off of it. So, if you have a camera driver that supports dynamic reconfigure, you can change the frames per second on the fly. So one thing that I do is I say, all right, I can log at 20 megabytes per second. So I'll open up a terminal and do ROS topic bandwidth on my topic, and then sit there with my slider and drag my frames per second down until I figure out where that bandwidth limit is and realize, yes, that's where I will not saturate my disk. And then I can save it and run it with that permanently. And then for changing a motor controller's configuration, this is probably a good idea because it will allow first-time users to quickly iterate through the different permutations that this may or may not support. But you should be aware that that could be dangerous, so hopefully your users have adequate emergency stops. And you should probably not use dynamic reconfigure for changing a publisher's topic on the fly, because that contradicts with the ROS remap of topics, which once you've changed that, it will cause all sorts of issues. And the last thing I'd like to talk about is diagnostics, which is something that all hardware drivers should try to support. They're very important because not all information is contained within the common messages that you see. So one approach is that people will create custom messages for this driver-specific information. And we've seen this really with GPS, because what's in sensor messages is a boiled down version that's specifically for clients that don't necessarily need to understand how GPS fixes work, just that they need the information on how to use it, such as the position and covariance. It doesn't contain things like the satellite count or the Doppler velocities. So the diagnostic system provides a framework to report these hardware statuses outside of your messages. So, and these can handle arbitrary measurements. So things like your GPS satellite counts, your encoder readings from your platform, your current system voltage, your disk space free, how much you're using your CPU. And then, so here's what's inside of the diagnostic status message. So the first thing you have is your component name, which could be just your driver name or what it does. The second element is your hardware ID. So this is commonly things like serial numbers or which internal unit it was or where it is on the vehicle if you have different encoders. The next thing is an arbitrary number of key value pairs. So you can push in things like your voltage or your modes or your current, and you can list as many of these in each diagnostic status as you need. And then finally, you have a human readable message that will tell your user if things are okay or not. So for instance, if your voltage drops below, say, 22 volts, you can say, ooh, the battery's low, I'm going to warn you about this. And speaking of warning, diagnostics also has many convenient levels. So the first one is, okay, everything's running as expected. The second one is warning, which means this behavior could affect operation, but it's not necessarily something you have to look at. So this could be if you lost your GPS base station. An error is a problem that needs immediate attention, so this would be if your battery voltage dropped below the level that's safe for your batteries, then you could alert your user that there's an error and that they need to recharge immediately. And then finally, in the tools, you'll see a fourth one known as stale, and then this is used when a node dies, drops, exits, or otherwise freezes, and you do not get new information. This is one of the diagnostics viewer tools. This is called Runtime Monitor, and this is the simpler of the two. So you can see here that on my computer, I just made a quick node that reports my CPU, my disk, and my network usage. And over here on the right, you can see the key value pairs between my utilization, my temperatures, and memory and swap. And then here's the other tool, which is Robot Monitor, which actually aggregates your diagnostics into different categories. So here you can see that I visualized CPU and disk, and while calculating Racine primes, my CPU temperature got above 85 degrees, so I decided to warn myself. Bad laptop. There are a few helper tools for diagnostics. C++ has had them for a while, and Python just got them. There's the diagnostic status wrapper, which just helps you fill in the messages with convenience functions. An updater, which periodically calls various callbacks, so you can, say once per second, go through and loop and make sure that everything's okay. And there's a diagnosed publisher, which tracks statistics. So if you use this publisher, it automatically tracks things like min frequency that you can accept and max frequency, and things like latency or time delays. So review on diagnostics, warn or error if you've lost 3 messages in a second, or if you've received no images in the last 30 seconds. And then finally, should you use diagnostics to actually disable your vehicle's motion? So if you've just lost 3 images, but they've resumed, you can probably diagnose that as a warning. Your system recovered and things seem to be okay. It may have just been a network or a camera hiccup. But if you haven't received images in a long time, that's an error state. And diagnostics should only be used to support logging and operator display only. The drivers themselves should actually implement any critical safety functions. Okay. And I guess I'll take questions at this point. The question was, is dynamic reconfigure tied to the GUI implementation, or are there other interfaces? And the answer is yes, there are other interfaces. At its base, dynamic reconfigure is a set of services that are called specifically for that node. So the GUI is essentially the minimal user human client for those services. Python currently has a code API, and the C++ one has been requested. Okay. So the question was, occasionally sensors output at the proper rate, but with nonsense things like a camera going instantly black or a laser scanner consistently outputting random noise. And where would you put this warning or error? So how I would do this would be in the diagnostic updater. You can set to have callbacks to check specific messages. So if you have a quick library that you send every laser scan through before it gets published, you could, for instance, check to make sure that the sensor was outputting appropriately. Although I guess this would be more appropriate for the camera, since you could detect all black pixels fairly easy, just with a quick random sampling, like especially in the middle of your frame. And then if that's true, once per second, it would check in and ask, oh, hey, have you seen this problem? And then you could report, yes, I have. So the question was, if you have multiple sensors and one of them has gone into a failure state, you wouldn't want to shut down your system until both of those have happened. And the answer to this question is that you shouldn't shut down your system from any particular driver, but only in very rare circumstances should the driver itself shut down what it's responsible for. So in the case of permanently damaging the hardware, the driver should be responsible for preventing that from happening, irregardless of what commands it's receiving. So this is things like protecting your batteries or current limiting if you can only, say, drive at max current for 30 seconds and there's no built-in hardware to protect it, then that's the sort of case where the driver should all of a sudden pull a stop. So the question was, should you bend the rules to make decisions based on the diagnostics messages? And the answer to that is that if it's critical enough, you should probably have a separate route to do so. The diagnostic system is intended for human consumption, which means you're free to, as the operator, to make decisions based on that information. But anything in a programmatic way should have more tests and more constraints to guarantee that if it is truly valuable enough to make decisions based on information, you should have a guaranteed critical path to present that. Okay, so there are very similar levels. The question was, when should you use ROS console versus the diagnostics? And the answer is that you should use both at the same time. The ROS console is triggered more or less on things that are immediate and have happened right now. So like if you fail a checksum or if your encoder all of a sudden skips an update, that could be an error. But in your diagnostics, it would be more accumulated problems, such as, well, the encoder has skipped 12 updates in the last minute. This means traditionally in our system that the encoder is dead and it needs replaced. Oh, this question. So one very common thing that we like to see is that we love these ROS console macros and we want to use them everywhere we can, but they're part of ROS and they tie directly into the ROS comms. So what do we do in our standalone library? Do we just print and hope that it makes it out, or do we throw exceptions and hope that whoever's implementing our library catches them? And the answer to this is that you can actually use preprocessor macros, right? That if ROS is present, you could print to the ROS console, and if it is not, then you can actually just print to terminal. I've seen this in libraries such as Octomap have done this very well. And so if ROS is present on your system and you compile it so, then you can actually use ROS console inside of the standalone library. But if someone's compiling it without ROS and without the associated flag, then it simply just turns into the normal standard out or standard error. And that's a pretty handy feature to use. So the question was, is if you have a large, complicated piece of hardware with its own software development kit provided by, say, the manufacturer, should you write a wrapper for that library and then have a node?
Basically, where do you put software development kits inside of do you put it with the wrapper, or do you need to find a way to include that in the operating system? That's libraries inside the operating system.
Okay, the question is, how do you deal with SDKs, basically? And the problem is, of course, is that they come from various manufacturers, and the quality can be high, it can be low, they can be buggy, they can be all kinds of things. They could force you to install, they could just be headers. So it really depends on your specific application. I've worked with a few, and I see them traditionally as replacing the library in my driver development stage. So I will use these as the library phase and just write a thin ROS wrapper across their library. And if they did a good job, I have an easy way to go. And I likely will have to change representations once because their library will support whatever data type they come with, and then I will just translate that to ROS and publish. And does that answer your question? Yeah. So it depends on the manufacturer. If they did a good job, your job's easy. If they didn't, look for someone else.